Okay, I'm going to get back to 5.1 and 5.2. We are talking about area at the moment, and I had defined a Riemann sum. Okay, a Riemann sum is just simply where you're adding up a bunch of rectangles in order to approximate the area under a curve. Okay, you got n rectangles, and either the left endpoints or the right endpoints are touching the curve, and ultimately, as the number of rectangles is going towards infinity, there's going to be less wasted space, and so the rectangles are going to be approaching the curve itself, going to get you the area under the curve. Let's take a look at, here's an example. We want to find the upper and the lower sums for the region bounded by the curve f of x equals x squared plus 1, the x-axis, and between 0 and 2. All right, so I've drawn a picture of that enclosed region there. We're between 0 and 2. We got this parabola shifted up 1 unit. And ultimately, a bit later in this problem, we're going to find the area of this enclosed region. Okay, now an upper sum just simply means that we're going to overestimate the area under the curve by drawing rectangles where the right endpoints are going to touch the curve. You can see I've got a couple of rectangles drawn where the right endpoints are touching the curve, and so I'm calling that an upper sum. Okay. Now, x sub 0 is always your start point. X sub n is always your end point here, so I'm going 0 to 2, and I'm going to basically build a formula that'll give me the total area of these n rectangles, which I'm going to call r sub n. R meaning right endpoints, n meaning I've got n rectangles. Okay, now the width of a rectangle is represented by delta x, and you take b minus a divided by n. So in this problem, a is 0, b is 2. 2 minus 0 divided by n, 2 over n would be the width of each rectangle. So like if I were to build, let's say 6 rectangles between 0 and 2, they all have the same width, 2 over 6, so each rectangle would then have a width of 1/3. Okay, and 2 over n would be just the general formula for finding the width. Now, I'm going to take the width times the height. The height is changing depending on where you're at on this curve here. So I'd like to see just, a kind of a pattern and maybe be able to produce a general formula that would give me the height of the ith rectangle. X sub 0 is 0, that's where I'm starting. Now x sub 1 would be where the first right endpoint touches the curve, and you can see that you're going to be at 1 increment of the width away from 0 to get to that first right endpoint. The width is 2 over n. X sub 2 would be where the next right endpoint would touch the curve, and you'd be at 2 increments of the width away from 0. So 0 plus 2 times the width. X sub 3, the third right endpoint, would be at 3 increments of the width away from 0, okay, etc. Now you can see that by this formula, whatever the ith rectangle is, it looks like you're going to be I increments of the width away from 0. So just a general formula for x sub I is going to be 0 plus I times 2 over n, or 2i over n. So if I plug that into the function, I would be able to get the height of that rectangle. Okay, so here'd be the setup here that would give me my my total area for when I have n rectangles. And this is what I'm calling a Riemann sum. Okay, just to verify that I would be getting all the rectangles, I'm going from I equal 1 to n. I'm using summation notation here. If I is 1, then the first height would be at f of 2 over n. Well, that's, 1 increment of the width away from 0 is what we said earlier. Okay, if I is 2, then you're going to be at 2 increments of the width away from 0. That looks good. Okay, etc. Now you're ending at n, so if I is n, and you plug that in, the n's would cancel, and you'd have f of 2. Well, here's 2. Okay, so in other words, at 2, that's where the last right endpoint would occur. That looks good. That's what I see. So in fact, I'm getting all n rectangles by this setup here. Now, f of x is x squared plus 1. So f of 2i over n would be 2i over n, the quantity squared, plus 1. And I can begin to simplify this now. 2 squared is 4. I'm dividing by n squared, and then multiplying by 2 over n. That's going to be 8 over n cubed, which is a constant. And I know constants can come out of sums. I'm going to go ahead and split this sum into 2 sums, and I'll pull out the constant. I've still got I squared, which has to stay inside the first sum. And then 2 over n, of course, is going to be distributed into both the terms. And 2 over n is a constant, so you can pull that out of the second sum if you'd like. Okay, and now we'll use our summation formulas here in order to lose the summation notation. So the first one, the summation is I equal 1 to n of I squared. That is n times n plus 1 times 2n plus 1 all over 6. And so that's what I've got written. And on this other sum, you're summing up a constant n times, the constant is 1, n times 1 is n. Be sure that you remove the summation notation. Okay, you've applied the summation formula to be able to do that. Now let's simplify. The n's will cancel there. 8 over 6, that's the same as 4/3. This n will cancel with one of the 3 n's in the denominator, going to leave me with an n squared. N squared is the same as n times n, and I can place each n underneath each one of these resulting expressions. N plus 1 over n, that would be the same as 1 plus 1 over n. 2n plus 1 over n, that would be the same as 2 plus 1 over n. Now, I'm writing it in that form because ultimately a bit later in the problem, I'm going to compute the limit as n approaches infinity of r sub n. Let's first take a look at the lower sum next. Okay, so lower sum means that you're going to underestimate the area under the curve. To do that, we're going to want to use left endpoints. Okay, I've got n rectangles here, and I want to draw them so that the left endpoints are going to touch the curve. Okay, and so I've drawn a few rectangles there, and I want to find the total area of when I add up all n of these rectangles, or what would that look like in terms of a formula. So x sub 0 is 0. That's where you're starting. Okay. X sub 1 would be where the first left endpoint touches the curve. Now that would also be at x equals 0. In the case of working with left endpoints, x sub 0 and x sub 1 will always be the same. Okay, since the first left endpoint is also going to be at your start point, wherever that is. X sub 2 would be where the next left endpoint touches the curve, and that's going to be at 1 increment of the width away from 0. Okay, the width is 2 over n, just as before. X sub 3 would be where the next left endpoint touches the curve, and you'll be at 2 increments of the width away from 0. Okay. As far as the ith left endpoint, it looks like whatever the subscript is on x, the multiplier is going to be 1 less than that number. Okay, so x sub I would be at I minus 1 increments of the width away from 0. Now, L sub n, that's my formula here that I'm setting up for left endpoints with n rectangles. Area of a rectangle is length times width. The width is 2 over n, so just as before, I'm going to keep that the same. Now the height of the rectangle is changing depending on where I'm at on the y-axis. So in order to find that height, the y value, I would just simply plug in the expression that I figured out here for getting me the ith left endpoint into the function. Okay. Let me check it out. So my sum is I'm going from I equal 1 to n. If I is 1 and I plug that in here, I'd be finding f of 0. Well, at 0, I'm going to have my first left endpoint. If I is 2, you get 2 over n. So the next left endpoint would be at 1 increment of the width away from 0. That looks good. You'll continue to plug in numbers then. Okay, if you plug in n, the last left endpoint would be at n minus 1 increments of the width away from 0. That looks good. That put me right here. Okay. So in fact, I will have gathered up all of these rectangles when I compute my Riemann sum here. In general, I don't know if you noticed, but if you compare R sub n to L sub n, in general, all you're going to do is you're going to replace I with I minus 1. Okay, and that should make sense because in the case of a left endpoint, you're just going to back up 1 unit to your start point. Okay, let's go ahead and compute L sub n now. We'll simplify. F of 2 over n times I minus 1. Okay, here's f of x. I'm going to plug that into the function. Yeah, 2 over n times I minus 1, the quantity squared, plus 1. And, okay, 2 squared is 4n squared times 2 over n. That's 8 over n cubed. That's a constant that can come out of my sum. I'll go ahead and split this into 2 sums, just as I did before. And I'll bring out the constants. Okay, 2 over n is a constant that would come over out of the second sum there. And I minus 1 squared, I can go ahead and FOIL that out. I've done that in the next line. And then I could split this sum into 3 more sums and use my summation formulas. Okay, so let me go to the formulas here now. The summation as I equal 1 to n of I squared, that is n times n plus 1 times 2n plus 1 over 6. And then minus 2 is a constant, I just leave that as is, times the sum as I equal 1 to n of I, that's n times n plus 1 over 2. And then plus the sum as I equal 1 over n of 1, that would be n times 1 is n. Okay, and over here, yeah, so the sum is I equal 1 to n of 1, that's n times 1 is n. Okay. These n's would cancel, okay, and now it becomes just a process in simplifying. So let's see here, these n's would cancel. Going to leave me with 2 at the end there. These 2's would cancel, and okay, 8 over 6, that's 4/3. This n can cancel with one of the 3 n's in the denominator. I'll have 2 n's left, which I could put 1 n underneath n plus 1 and the other underneath 2n plus 1. n plus 1 over n, that's the same as 1 plus 1 over n. 2n plus 1 over n, that's the same as 2 plus 1 over n. Now, 8 over n cubed is being distributed into these 3 terms. So this n can cancel with one of the 3 n's. That'll leave you with an n squared. N plus 1 over n squared, that's the same as 1 over n plus 1 over n squared. And then 8 over n squared times n, that's the same as 8 over n squared. Okay, and now I've got my answer in a simplified form there. Now, what if we compute the limit as n approaches infinity of r sub n? R sub n was up here, and so I've written that in such a form so that I can go ahead and compute the limit now. Limit of a constant is always the constant. Limit as n approaches infinity of 1 over n, that's 0. So you're going to have 4/3 times 1 plus 0 is 1 times 2 plus 0 is 2 plus 2. 8/3 plus 2, that'd be 14/3. Okay, now how about what if we had the limit as n approaches infinity of L sub n? Well, here's L sub n. Okay, and again, I've written this in such a way so that I can go ahead and compute the limit now as n is approaching infinity. Limit of a constant is always the constant. Limit as n approaches infinity of 1 over n, that's 0. So you're going to have 4/3 times 1 plus 0 is 1, times 2 plus 0 is 2, minus 8 times, these two terms would go to 0. Also this term would go to 0, plus limit of a constant is always the constant. So Okay, 8/3 plus 2 is 14/3. So A is 14/3. Okay. I mentioned here on the previous page, A is the area underneath the curve that we're trying to find. That's the limit as n approaches infinity of L sub n, which is also the limit as n approaches infinity of R sub n. Okay. In other words, the number of rectangles that you're making are increasing, and therefore approaching the curve itself going to give you the area underneath the curve. All right, and I've kind of summarized that here. So basically, as the rectangles increase, less space gets wasted, and so the area becomes the limit of the approximating rectangles. Here's a definition. Let f be continuous on a closed interval AB, and then divide that interval into n sub-intervals of equal width, which we're calling delta x. Delta x is defined as b minus a over n. Okay. Then for the ith rectangle with x sub I minus 1 less than or equal to c sub I less than or equal to x sub I, I'll talk about that in just a moment, the definite integral of f from a to b is the integral going from a to b of f of x dx equals the limit as n approaches infinity of the summation as I equal 1 to n of delta x times f of c sub I. All right. Now, in other words, the definite integral is defined as the limit of a Riemann sum. Okay, again, a Riemann sum is just where you're adding up a bunch of approximating rectangles. That's what I was doing here in calculating the upper sum and the lower sum. These are examples of Riemann sums. Okay, and c sub I is basically a number that's going to be inside of the width. Okay, now for the problems that we will be working with, it's either going to be right endpoints or left endpoints. But you could arrange the picture so that the rectangle will intersect the curve really anywhere in that width. You know, like there was one problem that we had looked at earlier where we were using midpoints instead. So if I go back to that, here's a problem where I was using midpoints. Okay, so just c sub I is either going to be a left endpoint or a right endpoint. Okay, and you can see that it's not going to matter which one we use because the limit as n approaches infinity of the right endpoints for n rectangles is the same as the limit as n approaches infinity of the left endpoints for n rectangles. We saw that in this example. It's in general that's going to be true. Okay, so that's and now we've talked about integral notation before. A definite integral is just simply an integral with bounds on it. Okay, and whenever this ends up being a positive number, you're computing the area under the curve above the x-axis and between two numbers. Okay. We'll take a look at some examples of that in the next couple of videos here.